Hello everyone. Today I am going to discuss about plasma dispersion. This plasma dispersion effect in metals, particularly in semiconductor, is very important. We use plasma dispersion in silicon waveguide for designing high speed modulators. So, we need to understand what is that plasma dispersion. It is nothing but basically the carrier concentration dependent refractive index or dielectric constant, and that is what we need to derive, and we need to concentrate on how electromagnetic wave propagates in a metals in semiconductors, contributing to certain kind of frequency dependent refractive index as well as frequency dependent losses. Let us see. So far we have learnt actually for a broad frequency spectrum, the optical properties in metal can be explained by the plasma dispersion model. Okay. Again, it's when I say metals, not like exactly metals, it's basically semiconductors also, which can be considered sometimes like a metallic properties. When you dope heavily, that also we can consider. So, in this plasma dispersion, where a gas of free electrons, we assume that it's a very heavily doped high concentration free carriers will be there, free electrons for example, that collectively moves against the fixed background of positive ion cores. That is true for both. It can happen for so called transverse electromagnetic wave as well as longitudinal wave we are considering earlier, that plasmonics wave can also take place. But transverse wave also can see some kind of electron motion in the vertical direction if you consider the wave propagation. So, three different interesting point you should note. First, the lattice potential, that means any crystal, whether it is metal and semiconductor and crystalline structures or whatever amorphous structure you can consider for metals also, but you see that there are some points where there will be heavy core ion will be there and surrounding electrons will be there relatively free. And this potential, that periodically in a crystal, whether it is a metal or a semiconductor, this positive ion cores will be there, and that will contribute for electron some kind of periodic potential. So, that potential and electron Coulomb interaction ignore for this thing, because there are you can consider that sometimes we have mentioned that it is a heavily doped semiconductor or lot of free carriers in metals are there. Normally their effect actually is dominant compared to whatever ion cores are there. So, that is why we can ignore for the moment. And electronic effective mass, to consider those type of electron free carrier like a never bound to the lattice points. So, we consider effectively, but of course, they are bound, and we need some approximation to consider them as a free carrier. So, that consideration is imposed on mass, which we will call as effective mass of electron, which is not equal to your mass of free electrons. That can be different inside the material electron mass. When you consider, of course, they are like a free. Okay, that is one type of model normally in semiconductor physics they use. And damping constant, when you are considering free, it is not completely free, again we are considering approximately free. If little bit damping is there while propagation, and that damping takes place because of collision, sometimes when it moves, and sometimes some collision happen because of the lattice heavy ionic points, and then that thing considered as a some kind of, you can say that time, average time or mean free time between two successive collisions it's called relaxation time or scattering time, and then you can say that collision per unit time, that is actually you can consider probability, collision probability per unit time is known as a damping constant 1 over tau. And electron conductivity we have explained earlier. Instead of n square tau by m, we are just considering effective mass. You can consider effective mass. N is the free electron density. Okay. This thing we have learnt earlier, this conductivity, I have just borrowed directly from there. And then you just think about electron motion under electric field. At you can consider z equal to 0. Normally electric field we consider E0 e to the power j omega t minus say beta z propagation direction. Normally if I consider a particular point z equal to 0, around z equal to 0, if you have a material medium, you just fix a coordinate point z equal to 0. In one dimensional case you are considering, and you can consider always this should be x, electric field is oscillating along x direction. Okay. So, in that case we can consider this equation of motion as this equation, where first one basically you are considering as a just mf, it is like a mf if there is acceleration, electron acceleration, one dimensional acceleration, that is a force, and because damping constant is there, so you can consider it is something like that dx by dt equal to velocity, and velocity by gamma if you are considering 1 over tau, that means m v by tau, that means rate of change of momentum per unit time, that is also contributing some force, and that force, that damping force as well as free movement force, total accelerating force together actually coming because of the force imparted by the electromagnetic wave. That means, if you have a electric field on charge A q, then force is equal to, we know that q times E, and normally if it is electron, it is a negative direction. Electric field, if it is positive direction, electron will tend to move in the opposite direction, so opposite force will be there. So, that is why negative sign is there. Alright. Now, what would be the solution of this equation? Just we are considering at z equal to 0 and we are focusing only one electron. What happens to one so called free electron? What happens? That has some kind of damping constant will be there, and force will be there because of the electromagnetic wave, and this one we can consider here, and this solution we can consider something like this, one dimensional case. That is why I am not considering the vector here. So, if you consider this one, you substitute here. So, what you get? You get here, after substituting you can find what is the value of x0, because we have assumed that this electric field when it is in motion, x0 whatever time dependent thing also will be this one in this case, and in this case x0 can be a complex. Just if you substitute here, it is coming like a complex. Okay, you substitute here and then you can find out e to the power j omega t. For example, here you will be getting dx2 by d2. So, mn here, and then you can have x0 and minus j omega square, and then e to the power j omega t, and then this one will be mn gamma and minus j omega and x0 e to the power times e to the power j omega t, and right hand side your minus e0 e to the power minus j omega t, e to the power minus j omega t, e to the power minus j omega t, and minus j omega t cancel. So, in that case I can find out x0 value here, x0 here. So, x0 e0 right hand side e0 divided by this one, minus sign will be cancelled. Okay. So, now with this x0 is there. Now, what we get? What would be the xt value? I just put this x0 here, then I get xt equal to this one, right. E0 times e to the power j omega t, I can write this one, time dependent. Now, you you may not consider that it is only one frequency, it can be time dependent, whatever electric field is oscillating, and of course, frequency is there. So, you can write frequency domain, at certain frequency you will be writing something. Fine. Now, what is this? This is actually, we know that suppose a positive ion core is there and electron is moving in certain direction, x direction it is moved. This is electron position here. So, this is plus, this is minus. So, x position displacement is there. So, in that case it is a dipole, and dipole, you know, whatever the charge is there, charge is E and displacement is x, and dipole moment is, for a particular atom, dipole moment is charge times momentum, and this negative sign is that because dipole moment direction is in the opposite, because electric field, if you give one direction, normally dipole moment we consider positive to negative in the opposite direction. So, negative sign minus Ex. Now, if you are considering this is only one electron you are considering, if there are electron density of n, then you can have n times Ex, that is the dipole moment per unit volume. N is the per unit volume density of number of electrons, electron density I would say n. So, this is the n. So, I have x solution is there. We are considering all electrons are moving like this collectively, that type of displacement happening. So, in that case I can substitute this x value here, then the dipole moment per unit volume is called as a polarization density. That polarization density comes into your Maxwell's equation. So, I have just written polarization density equal to this one, that is actually for a given frequency it is proportional to E. So, this type of things we are considering that polarization density is just linear to electric field. We are just considering all solutions are here now linearly dependent. Okay. This solution, simple solution is coming like this. Now, I have just written down that one here, same thing, polarization density, and now displacement vector, we know that displacement vector is this one, epsilon 0 E, what is coming from external things, and P, polarization density. P is this expression. So, it is simply you can modify like this too. Straightforward, just putting here, P you are putting here directly, minus sign is there, epsilon 0 will be common, right. So, then epsilon 0 comes here, Mn, that is fine. Now, so if I just think that d equal to epsilon 0, epsilon r E, that is d equal to epsilon E we write, right. So, that means I can write epsilon r from here, if this one is the epsilon r, d equal to epsilon 0, epsilon r E. So, epsilon r will be this one, just within bracket whatever is there, that is actually epsilon or dielectric constant of 3 electron with some damping constant is there, you have considered, right. Now, we just consider, because numerator if you see here this thing, they are actually all are fundamental constant, only thing is that density, number of electron density, that is given there. We just consider that is actually omega p square, this one is omega p square, will come that is actually known as plasma frequency. Why it is called plasma frequency, that will be clearer after some time. Okay, if we consider that, we get a very nice equation like this, omega p square. So, omega p square, of course, it is actually proportional to number of carrier density. So, carrier density more, omega p will be more, that is fine, right. Now, we know that this gamma equal to 1 over tau, already earlier discussion we have mentioned, right, and then this is epsilon r, and you see this is a complex. So, we can decompose into real part and imaginary part, okay, and a little bit of maths, one step algebra, you can find whatever the real part and whatever the imaginary part, epsilon 2. In terms of omega p tau, I have just replaced gamma as 1 by tau, fine. So, we have real part, imaginary part, just you have to multiply here omega 0 minus j gamma omega, then you can get denominator is the, you can decompose real part and imaginary part simply, and real part will be like this and imaginary part will be like that, straightforward. Okay. I multiply this one in the top and also I have to multiply this one in the bottom. Okay. Good. So, now we will be considering a certain regime omega tau larger, much larger than 1. That can happen if gamma is gamma equal to 1 by tau is very small, or omega frequency is very large. Whatever the things, if you just consider omega tau much larger than 1, typically it can happen also, very large frequency we are considering. Then in that case, this omega tau, this is very large, this 1 you can ignore, this 1 you can ignore. If that is large, omega tau is much larger, right. So, in that case, this one will be reduced to, so I can ignore 1. So, omega square tau square cancel, omega p square by omega square, this one will come. And here if I ignore 1, then omega times omega square, omega 3. So, omega p square by omega 3 square, and then tau will be cancelled. So, we will be getting 1 over omega tau. Okay. Omega p square, oh here 1 omega is there, that should be omega square. For electromagnetic wave, if you are considering omega greater than omega p, this is approximately equal to 0 because this is actually very large. So, you can just reduce to imaginary part can be smaller. Only the dielectric constant will reduce to real part only, like this one will be dominating for example, for this type of situation if it happens. And if omega greater than omega p, that means this will be less than 1. So, in that case your electromagnetic wave will have some dielectric constant which is completely real, and if it is completely real, then refractive index also will be real and it will be propagating, electromagnetic wave will be propagating without any loss. So, that is why it is called electromagnetic waves. That means, you need to have omega at least greater than omega p. Omega p can be calculated like this. Okay. So, you can get your plasma frequency, so called a certain frequency greater than plasma frequency, your electromagnetic wave can propagate without any loss. It is a transparent, that is interesting. Now, other regime we are considering. Up to here it is same, and instead of omega tau greater than 1, very small frequency if you are considering for example, or certain region tau is there, tau value is there, that is somehow less. So, what we can consider in that case, if it is small, this part we can ignore, this part we can ignore. Okay. If we ignore that, then this real part will reduce to this one and imaginary part will reduce to this one. In this case, if you see, okay, omega tau, that means omega is much lower, that means epsilon 2 will be much higher compared to epsilon 1. So, if you consider epsilon 2 much higher compared to epsilon 1, then earlier you know that n square expression we have derived earlier, because square root of epsilon r equal to, we can write n1 plus j kappa, and that is why epsilon 1 and epsilon 2 you can relate with the n and kappa, and there we have derived what is the relationship between n square and kappa. Since epsilon 2 is much greater than epsilon 1, this expression for refractive index, real part of the refractive index can be approximated as, so we can put this one cancelled, this one cancelled, so epsilon 2 by 2 approximately, because epsilon 2 is dominating, and kappa we know epsilon 2 by 2n. So, n value is the square root, n equal to square root of epsilon 2 by 2, because n square expression is this one. If you just put kappa also same. So, that means you are getting n and kappa will be same in this particular case. So, what I mean to say that when omega is somewhat very small, smaller frequency, very long wavelength, for longer wavelength case, this kappa and n, real part and imaginary part of the refractive index, they are almost similar. Okay. This is little bit reverse situation I am considering. When epsilon 1 less than much lower than epsilon 2, that is what we have considered earlier, then n equal to kappa equal to same thing, both are same, whatever it is. Now, epsilon 2 value, I have this one, I just put down here, square root of omega p square tau, and 2 is there, 2 times omega, I have just put down. And now, next thing is that alpha, alpha we know that is the attenuation coefficient for the electromagnetic field propagating inside the material, that is 2 pi by lambda times kappa, or omega by c, that is also we have derived, c multiply 2 pi c by lambda equal to omega, and c will be there, this one, and omega c and kappa expression we put down here. How, what we have put? Omega by c, kappa equal to this one, and omega p expression is this one, omega p square. If I just put down, what I get? I get very nice equation. So, alpha expression is reduced to this one, let us put simplification, what you get here, this one. So, mu 0 epsilon 0, epsilon 0 epsilon 0 cancel. So, omega sigma mu 0 by 2, that is alpha. Alpha is attenuation coefficient, you know that, E equal to E 0 e to the power j omega t minus beta z e to the power minus alpha z. So, amplitude, how it is attenuated as it propagates. So, attenuation coefficient we find this one. You recall lossy medium. Lossy medium you recall earlier we have discussed gamma equal to alpha plus j beta, space dependent electric field in Fourier domain we have solved, and alpha expression for lossy dielectric medium, this one, and beta we have solved this one, right. And then for sigma is very large, if you are considering infinity, sigma tends to infinity means if it is large, or maybe you can consider sigma is greater than omega epsilon, okay, some value is there, then I can ignore this one, compared to this one, then alpha value will be, right, alpha equal to beta equal to. So, basically at lower frequency or very high conductivity, that regime, the alpha value, real part of the propagation constant and imaginary part of the propagation constant, they are identical. Okay. So, skin depth, when it is propagating e to the power, for example, e equal to, you are writing E 0 e to the power j omega t minus beta z times e to the power minus alpha z attenuation coefficient. Z equal to delta 1 by alpha beta, that is actually we can consider Z equal to ZD equal to alpha 1 by alpha, then this will become 1 over e to the power minus 1, that means your amplitude will drop 1 by eth. Okay, 1 by alpha distance, if you find 1 by alpha, alpha is the per unit length, whatever the attenuation. So, 1 by alpha distance if travels, then your amplitude will drop to 1 by e. That is actually called skin depth. That electromagnetic wave, shorter frequency or very high conductivity, if it travels, high conductivity, and you can have an optical frequency also, then you can think of the optical frequency after traveling to this much length, it will be attenuated to 1 by e, that is called actual skin depth. So, if you have a source material medium, it cannot travel fast depending on this value. That means, if your sigma is very large, in this expression if you see sigma is very large, then your delta will be small. Otherwise, suppose sigma is fixed, if you are increasing your frequency in that regime, then your delta also will be small. Higher the frequency, it cannot penetrate. That is why optical frequencies, if you see in the metal, it normally reflects. It does not cannot actually propagate longer distance. Okay. So, same thing here we say that this is actually alpha, whatever you are getting here, this value and this value same, and skin depth we can just find out. In the two different treatment, we have used lossy dielectric medium, there also we can find out what is the skin depth, whatever expression you get, and here considering plasma dispersion effect, also you get similar expression for the propagation constant, loss coefficient I mean to say. Okay. Now, refractive index at higher frequencies. I would like to find out now refractive index. Loss coefficient is fine, but refractive index we can express like this, right? And that can be just consider square root of epsilon r. Dielectric constant, whatever dielectric constant you get, square root of that, you will get the refractive index. Okay. So, I have written this one some little bit differently, I am just considering. You just assume that okay, for higher frequencies this gamma, that means this damping coefficient is small compared to your frequencies. Then here if you are just putting gamma equal to 0, so omega square will be very large. So, in that sense this part I can ignore, then I can obtain this expression, that dielectric coefficient that can be expressed as frequency dependent 1 minus omega p square by omega square. Okay. So, now what is happening? I know that for transverse wave the dispersion relation k and omega relationship we can find out, we have already discussed earlier, that is actually k square equal to omega square by c square into epsilon omega. I know that. Okay. So, if I use this one and from this expression if you insert this one, then you get this one, this expression you get, because epsilon omega, if you just write here epsilon omega equal to k square c square omega square, that means I am just writing k square c square times k square c square divided by omega square, right, omega square equal to 1 minus omega p square by omega square. So, this part is nothing but I am getting from here epsilon omega k square c square by omega square, and right hand side 1 minus omega p square omega square. So, I can write this one equal to k square c square by omega square equal to omega square minus omega p square by omega square, omega cancel, and then k square c square plus omega p square equal to omega square. So, omega p square k square c square, that is the expression I have written here. Okay. And that one you can actually write, if you just divide normalize by omega p square, then omega over omega p whole square, and this one will be 1 k c by omega p square, that is the what expression I get. So, this expression I am just considering that okay, you are considering at higher frequencies I want to find out the refractive index, and that refractive index I am just starting from this, whatever the plasma dispersion I have considered, polarization, density, all these I am just putting down here and I am getting this thing. And then if you see this expression if I just try to plot, how it will be looking like? You see this y axis is omega over omega p, that means this one actually we can write y square is equal to 1 plus x square. So, when x equal to 0, y square y, yes, I will be writing y equal to square root of 1 plus x square. Yeah, when x equal to 0, y equal to 1, we are putting there. So, for omega by omega p exactly equal to 1 there. So, this means this point is omega equal to omega p exactly at so called plasma frequency. So, so called plasma frequency, then omega by omega p 1, then k c by omega p, that will be 0. So, that time nothing is happening. So, exactly k is actually appeared to be 0. So, you will be getting this equation. If you plot, you just vary. Omega p is a constant. This is a constant value depending on the concentration square epsilon 0 mn, you get a constant value. Just put down here, then you get a dispersion relation. Now, if you see in this expression, omega by omega p equal to kc, and this curve, if you see here, whatever value the ratio, this is non-linear basically. So, I can say that as a function of frequency, your propagation vector k is going to change, wave vector is going to be changed. So, normally at any point, if I just try to find out d omega by dk, that is actually called the group velocity. So, group velocity here is very small because slope is less. D omega by dk, if you are just considering this one and this one, at any point you just take a slope here and then you get a group velocity and lower, and slowly it will be increasing. And then one interesting point is that in this case I have just taken this picture from a textbook. This is called light line. What is that light line? That means this omega p and kc by omega p, they are actually showing linear. So, every point d omega by dk is nothing but omega by k, right. Omega by k equal to d omega by dk omega by k, which is the slope will be, that is nothing but c, that is the velocity of light. So, normally this is the light line. Whenever I am considering that any point d omega by dk or omega by k, they are same. Omega by k will be, if I just take a slope, this omega by omega p divided by kc by omega p. So, omega p cancel, and omega k by omega by k, c will be the slope. So, in that case you will be getting a linear, that is when you are considering light line. That means, when the light wave propagates in free space, if it is free space nothing, then it will be just omega versus k, dispersion relation will be like this. Okay. But inside material medium it is looking like this, it will follow this type of. So, in that case it is highly dispersive. As a function of frequency, your wave vector is dramatically changing, particularly at exactly at omega equal to omega p. If you see here, exactly at omega equal to omega p, your epsilon omega will become zeros. And we have learnt earlier that when dielectric constant is 0, in that case no transverse wave exists. Instead of that, longitudinal wave comes into picture. So, electron, the wave will be propagating as if it is not like a transverse wave, electromagnetic wave will be existing, as you will see that electron wave will be oscillating, as a collectively it will oscillate. That is actually called plasma oscillation, and that is the reason this omega p is called plasma frequency. Okay. Now, this is nice. So, we have discussed that considering your dielectric constant because of the free electrons, free carriers, considering sigma, how is the polarization, it is polarization density created because of the displacement of electron motion we have considered under the influence of electromagnetic wave. But in practically, you know, it is semiconductor, for example, or metal, heavily doped semiconductor, you have plenty of free carriers are there, but apart from that you have actually practically you have the ion core. This ion core will have, it can also create some kind of dielectric polarization, separate, it can be completely separated from your valence electrons. So, core electrons that can also create some kind of local dipole moment. Okay. So, that local dipole moment can contribute to your dielectric, overall dielectric constant. That is the reason, even though we have just discussed plasma frequency, plasma oscillations, everything, but actual metal if you just consider, then you will see that this core actually contributes some kind of dielectric constant. That is why this equation, whatever we have derived here, polarization here, this particular thing, dielectric constant, this is supposed to be epsilon r, that needs some modification. And that modification, experimentally it is found that some value we have to add instead of 1, so called epsilon infinity. Typically it is found that it should be within 10, 1 to 10 it is. It must be more than 1, because that is actually additional dielectric constant is contributed because of the ion core. So, we can have this one, the expression can be modified like this. Why it is infinity? If omega tends to infinity, whatever dielectric constant is there, that means at very high frequency, then right hand side will be completely negligibly small. So, the effect of plasma, all those type of things, this part will go. So, whatever left over, that we call as a dielectric constant E epsilon infinity. So, your actual expression will be like this in practical situation. In this simple model, whatever we have considered, the plasma dispersion model, ion core we have not considered, contribution of the ion core, just to get the contribution, but you should know it is a kind of model, but the practical situation there will be something like that. So, with that model, you can fit with a experimental results. For example, here it is a gold material. I have taken again from the textbook. Gold material, if you see this dielectric constant, actual dielectric constant as a function of frequency. Frequency means energy here. We are just considering energy. When frequency is omega, then photon energy h cut omega. So, this h cut omega energy is called energy of the photon, electron volt. So, 0, 1, 2, so on. So, about 1.12 electron volt, here actually it is lambda equal to around 1550 nanometer wavelength. That is the third communication window, optical communication window. Okay. So, 1.12 or so on. Now, if you see that when your energy is being increased, more and more energy is increased for gold particularly, okay, then what happens? You can actually find imaginary part as well as your real part. So, this one it will have a real part, imaginary part, along with that epsilon infinity will be there, that is more than 1, but less than 10. It can be higher than 10 also, something like that. So, if you just add the real part from here and here, combine that together, as it is increased, energy is increased towards the visible. This is 1550 nanometer, and you are increasing energy means your wavelength is decreasing. That means you are going towards visible. Then you see that experimental result says that real part of the dielectric constant is actually happening negative value, and around this point, this is the value here about 3 electron volt or so, this is actually almost saturating, higher energy it is saturating to 0. Some model it is fitted with here, it is showing like this, but practically when you measure, the real part is almost close to 0, what is happening. So, when close to 0, what is happening? For higher energy, as a higher frequency when it goes, that time it is something like that, real part is 0. So, you can see like a some kind of zeros, real part 0 means basically it cannot propagate, only imaginary part will be there. That imaginary part here it is shown here. Because of this imaginary part actually you can see that will be attenuated, and that imaginary part also you can see as a function of energy, this is actually dropping like this, but you will see certain kind of experimental measurement, these dots, these are actually experimental measurement. This experimental measurement shows that imaginary part is increasing at higher energy, and that cannot be modeled with this one. This happens because of the interband transition. Within the band, the high energy photons will be absorbed by electrons, and it can also create it can see some losses. So, this is basically absorption, photon will be destroyed and electron will be it will capture the photon energy to get its own higher energy within the band. That is why it is called interband transitions. So, this is the real part of the dielectric constant, this is the imaginary part of the dielectric constant. And you can also measure say refractive index also, because square root of epsilon r is equal to n, this one that can be considered as this one. So, this n omega, if you are seeing, this is for gold again, for material, metal, this is also gold. From the textbook this picture I have taken. You see the imaginary part actually, it is real part of the refractive index, it is dropping as you increase the energy. As you increase the energy means you are actually decreasing the wavelength. So, this is actually called dispersion, actual dispersion, that is extracted from the results shown from here. So, whatever value you are getting here, this model, using this model you can extract using this expression real part of the refractive index, it is showing like that, and imaginary, that is called extinction coefficient, you know, alpha equal to 2 pi by lambda times kappa. If you know the kappa, then you know the attenuation coefficient, and then from the for the Beer's law, what is the loss coefficient, loss constant you are getting, that will be 4 times 4 pi by lambda kappa. So, once you know that, then you can find that okay, how it will be attenuated. So, this is shown for gold. Same type of consideration you can consider for semiconductor, for silicon also. If you are just considering silicon, crystalline silicon or intrinsic silicon or conducting silicon, little bit of doped silicon, if you are using as a core material for waveguide, for example, for photonics integrated circuits, in that case also if it is doped or carrier concentration, if you are increasing, conductivity you are increasing, then also you can see this type of loss and refractive index. Both you see, you can have refractive index, real part of the refractive index and imaginary part of the refractive index, both actually depends on this value. And in this value, if you see, n is there. What is that? Carrier concentration. That carrier can be free electron, that can be free holes also. Okay. So, for a given n, you can have a certain value. For example, you are operating at a energy here. It is you are considering, for example, silicon, not gold, for example, and you know that you have a refractive index, certain refractive index. Now, if you change the concentration, then the real part and both the real part and imaginary part will be changed. So, that means your real part of the refractive index also will be changing and imaginary part of the refractive index also will be changing. So, that particular property is very much you can exploit, particularly in semiconductor. Semiconductor, you know, you can actually have some kind of diode junction, and junction region you can actually control the carrier concentration by bias control. So, if you can give a bias, electrical bias, you can control the carrier concentration, and if you can control the carrier concentration, both real part of the refractive index and imaginary part of the refractive index can be changed. Real part of the refractive index change result into a phase change, and imaginary part of the refractive index change result into a loss. So, that means you can actually control the carrier and you can control the loss coefficient as well as refractive index, phase constant. Phase actually can give you some modulation, phase modulation, and this one so called extinction coefficient control can give you attenuation. You can have a variable optical attenuator. So, this is the basic thing is exploited for photonic integrated circuit using CMOS compatible silicon photonics platform. Okay. So, very important when we will be discussing photonic integrated circuit, particularly modulator, where actually you convert electrical signal into optical signal. When you design a modulator, that time this thing actually very important. You have to think about how to control the carrier and how to control the refractive index and how fast you can do that. That is how modulators are designed.